I promised I would make a little video about this bonding quiz that some of us aced, but not all of us aced. And so what I wanted to do is make a review quiz for those people who would benefit by taking a little time to study it. So we're just going to go one by one through the questions. I have a few resources up here at the top of the screen that we'll refer to as we go. So question number one asks us to pick from this list of dot diagrams which one has a trigonal planar electron geometry. Now, a trigonal planar electron geometry is different than a trigonal planar molecular geometry. You can have, if you look at this chart, you can have a trigonal planar electron geometry and have a bent molecular geometry. So we're looking for the electron geometry column. So let's take a look at some of our choices. We had choice number one was we had 9, 16, 17, and 4. 9, 16, 17, and 4. So we'll mark them on here. 9, 16, 17, and 4. So we'll just start drawing our dot diagrams. Now I'm going to assume that you know how to draw dot diagrams, and I'm going to explain them, but I'm going to explain them kind of quickly. I'll refer you back to this page, January the 5th, where I have a video help on how to draw dot diagrams, and this is a pretty detailed video involving the drawing of dot diagrams, and I've laid out the directions pretty carefully. So you might want to spend 20 minutes or half an hour studying that if you're wondering about how to draw the diagrams. All right, so we'll do PCl5. PCl5 has got 5 valence electrons in phosphorus, 7 in chlorine, but there are 3 chlorines, so you're going to need to multiply it by 3. I'm not going to show you this for every molecule either, but here we go for the first one. See, phosphorus is in the 5th column. Remember, it's 1, 2, all these have 2 valence electrons, and then 3, 4, 5, 6, 7, and then 8, except for helium, which only has 2, but everything else in this column has 8. So phosphorus has 5, chlorine has 7, and that's where I got those numbers. When I refer to the number of valence electrons, that's how I get them. I just look at the periodic table and say how many electrons there are. Okay, so we've got 5, 7 times 3 is 21, so we've got 26 total valence electrons. We do a P in the middle. Now, in the other video, I explained to you fairly in detail how to know what goes in the middle, but basically there are 3 things to consider. One is which one of these 2 elements is closer to the middle of the periodic table. That's phosphorus. The second thing to consider is which one of the 2 elements has more open spots. Well, phosphorus has a dot diagram that looks like this. There's 5 valence electrons, so it has a spot here and a spot here and a spot here because it could have 8. So there's 3 open spots. Chlorine, on the other hand, only has 1, 2, 3, 4, 5, 6, 7. Has 7, only 1 open spot. So phosphorus has more open spots. And the third thing is less electronegative. And so if you look at what's less electronegative, as you go to the right, they get more electronegative, and phosphorus is less than fluorine in terms of electronegativity, back from first semester. So we know that phosphorus is going to go in the middle of our dot diagram. So we set it up like this, and we put the CLs here, and we take away 6 electrons because each line counts as 2. It's a bond, it's a shared pair of electrons. So we end up with 20 loose dots to put in. So I start putting them in so that everything has 8. 2, 4, 6, and these 2 make 8. 2, 4, 6, and these 2 make 8. 2, 4, 6, and those 2 make 8. So I've put in 18 of the 20, because I had 6 in there, gave me 20 to put in. I put in 18, so the 19 and 20 go there. So how many domains do you have? 1, 2, 3, 4 domains. And remember, 4 domains, that's a tetrahedral electron geometry, not trigonal planar. So that one is not the answer to our question. Our question said, which one has a trigonal planar electron geometry? So we draw the next one, HCN. HCN. And we have 4 and 5 makes 9 and 1 makes 10. So when you draw the dot diagram, it's going to have to look like this. How many domains? 2. You have to have 3 domains to be trigonal planar, so that's not it. SO3. Put S in the middle. Now S has 6 valence electrons. Oxygen has 6. There's 3 of them. So they have the same number of valence electrons, which means they have the same number of open spots. But sulfur is less electronegative and closer to the middle of the periodic table. Okay, set up our skeleton structure. Take away, 6 times 3 is 18, plus 6 is 24 valence electrons. Take away 6 gives us 18 to put in. And now I'm out of dots, but I still need 2 more dots here. So I am 2 electrons short. If you're 2 electrons short, you have to add a double bond. Now, when I have 24, but I take away 2, 4, 6, 8 electrons, which gives me 16 to put in. And here I'm putting in 16 dots, and now everything has 8 around it. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, and 2, 4, 6, 8 for the sulfur. Notice that these lines count for both the oxygen and the sulfur in every case. So since they are shared electrons, they count as being 2 electrons for every atom to which they are attached. All right, how many domains? 1, 2, 3. 3 domains, trigonal planar, and that's your answer right here, trigonal planar. So that was the correct answer for that question. If you want to see it in real life, let's draw a picture of it. Take that away, take this away, take that away. Oh, don't need that. Take that away. Can't take that without this. Put that on. Take this off. And this is what trigonal planar looks like. There's no unshared electrons around that center atom, so it just goes flat in a triangular plane. If I did have an unshared pair, see, that makes it go into a pyramid. But the unshared pair is not there, so it's planar. All right, next question. Which molecule's bent? So 4, 9, 5, and 29. 4, 9, 5, and 29. Okay, we've already drawn 4, and it's not bent. There's 4. It's a pyramid. We've already drawn 9, and it's linear. It's a straight line because there's nothing around this center atom to cause it to bend. Just showing you that real quick. Here's what it looks like. All right, so it'd be a straight line like that. There'd be an unshared pair of electrons out here that we're not seeing in this picture. And if you want to see the bond angles, that's 180. All right, so that's a straight line. We didn't draw 29, let's do 29. So IBr2 with a +1 charge. We'd have 7 plus 7 times 2 is 14. So we end up with 21 valence electrons, but the +1 charge means we've lost 1. So we take away 1, and that gives us 20 valence electrons. So we're going to put an I in the middle and a Br out to the sides. And the reason for that, again, I is less electronegative than bromine, a little closer to the center. They both have the same number of bonding sites. So I take away 2, 4, and that gives me 16, no, I had 20. Take away 4, yeah, 16 to put in. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, uh-oh, what did I do wrong? 7, 14 and 7 is 21. Take away 1 is 20. 20 minus 4 is 16. 2, 4, 6, 8, 10, 12, 14, 16. That works. 2, 4, 6, 8, 10, 12, 14, 16. I just miscounted. So that's our picture. Notice there are 4 domains. So 4 domains means that it's tetrahedral. And it's not only it's tetrahedral, but 2 of the domains are shared and 2 are unshared. So we're right here, 2 and 2. So the molecule's bent. And here's what it would look like. It has 2 shared and 2 unshared, and so you can see the bent structure, like that, bent. So that was our answer, the IBr2, and that was question number 2. So you can see the answer was number 29, the IBr2. Okay, this one wants to know which one's T-shaped, so we're looking at 22, 17, 24, and 1. I'll mark them over here, 22, 17, 24, and 1. So if you draw number 1, it's going to look like number 4. You might remember drawing that in class, so I'll just do this real quick. That's what its dot diagram will look like. What were the choices on that? Number 1, 17, 24, and 22. Let me circle these. 17, 24, and 22. All right, we're looking for T-shaped. All right, I'm going to draw 24, and we'll do that one next. So here's number 24. 24 has CLF3. So CLF3. And 7 times 3, 7 times 3 is 21, plus 7 is 28 valence electrons. In the middle of this picture will have to be chlorine because it's less electronegative than fluorine. And again, if you don't know what that means, just look over here. Chlorine's less, it's lower down, so electronegativity increases as you go up. So put Cl in the middle. All right, and take away 6 of the 28, so that gives us 22 loose dots to put in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Now I got a problem because I still have 2 more. Notice that I am not 2 electrons short. I have 2 extras. Extras go on the center. So around the center now I'm going to have 5 domains. So if we make it, I'll make a model of it. There it is. So I've got 5 domains there. See, 1, 2, 3, and then 2 unshared. What's that molecule look like? So that's your T-shape. Or you can tell by looking here. When there's 5 domains, when there are 3 shared and 2 unshared, it's called T-shaped. So the answer to that question is number 24. Number 24 was the one I just drew, CLF3. Okay, this one says which molecule's flat. So we're going to do 1, 3, 19, and 25. So 1, I'll put them in triangles. 1, 3, 19, and 25. Okay, I'll change papers here in a minute. So I've already drawn number 1. We're looking for the flat molecule. Here's number 1. That's not going to be flat. That's a pyramid. And take that off, and there it is. There's your pyramid. 3 shared and 1 unshared. Number 5 I've not drawn. I'm going to build it right here. So that's what it looks like when you build it. If you draw it, it looks like this. So you got a C and O's on the outside. Take away, you got to add up your valence electrons. 4. 6 times 2 is 12. 16. So take away 4 gives you 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm out of dots. Oops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Apologize for getting off the screen there. So I need 2 more dots here. I need 2 more dots here. So I do not have them. I am 4 short. 4 short. I need 4 more. So if you're 4 short, we said what you do is either add a triple bond or 2 double bonds. Generally, you want to keep it symmetrical if you can. You can't if one of these atoms is hydrogen, but here we can. So we take away now 2, 4, 6, 8 from our 16, which gives us 8 dots. 1, 2, 3, 4, 5, 6, 7, 8, and that's our picture. So you notice there's only 2 domains, and 2 domains is linear. Linear means a straight line, so that's not flat. We're looking for the flat molecule, so we know it's not number 5. I shouldn't have done 5 because it was not one of the choices. I just went by the wrong one. So let's take a look now back at number 3. So here's 3. 3 is H2O. We'll put an O here, put the H's out here. And when we add up our valence electrons, we got 6, 7, 8. Take away 4, gives you 4 to put in. They don't go on the hydrogen because the hydrogen's happy with 2. I'm going to have to repeat that one because I forgot that I wasn't on the screen. So here we go. I've got to click back. So hydrogen's H2O. You've got 1 times 2 plus 6. Take away 4. So that gives you 4 to put in. So 6 and 2 makes 8. Take away 4. Gives us 4 to put in. They go around the O. They can't go around the H because the H is happy with 2. Okay, so let's make that molecule, see what it looks like. It has 2 lone pairs. So on the sheet, it'll tell you that that is a bent molecule. It's tetrahedral, right here, with 2 shared and 2 unshared. So it's a bent molecule. But if you look at it from this angle, it's flat. See, it's just flat right here. You don't count the unshared pairs. So that's the answer to this one. The flat molecule was number 3. It was water. Number 19 and number 25, if I do a quick look at those, 19, SF6 will end up looking like this. Definitely not flat. Okay, so that's going to be this. It's called an octahedral. Looks like this. Like that. So definitely not a flat molecule. And the other choice was number 25, which was CLF5, which we already drew a minute ago, and that was the T shape. All right. Change papers, clean it up a little bit. Okay, next question. Which molecule has only 1 pi bond? Well, let's take a quick look at something I've already drawn. We'll come back to the messy one. This guy has 2 double bonds. Every double bond includes a sigma and a pi bond. So every double bond includes a sigma and a pi. So sigma pi, sigma pi. Remember what the pi bond is. If I do this C right here and do the 2 orbitals that are around it. Here's your H hanging out like here. Here's another C over here. Let me redraw that. So I got a C like that. It has 2 orbitals around it like this, and the hydrogen's over here. Here's another C like that, and the hydrogen's out here. So there's the H, there's the H. And this is called a sigma bond. The pi bond, remember the hands and the feet and the trash can? That's the pi bond, the hands and the feet, just one bond. So if you, and this is all together, all this stuff right here, that's a double bond. If I had a triple bond, there'll be another one of these hands and feet perpendicular like that. So when you have a double bond, you've got a pi bond. When you have a triple bond, you got 2 pi bonds. All right, so our choices on this one, going back to this question, which has only 1 pi bond, wouldn't be number 5, because number 5 has 2 pi bonds. The next choice was number 11. So let's look at number 11. Haven't drawn it yet, so you have to, if you do that, it's a CO like that. 6 and 4 makes 10. Take away 2, 6, 7, 8. So that's 2, 4, 6, 8, 10. We still need 2 here and 2 here. We're 4 short. When you're 4 short, you add a triple bond. Take away 6, put in the 4. So that has 2 pi bonds. So that's not the answer either. We want only 1 pi bond. Next one was 15 and 22. So 15 and 22. Let's look at those. 15 is XeF2. It's going to have extra electrons. 7 times 2 is 14. So we're going to do F here. We'll do F out here. Take away 4 gives you 18 to put in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It's going to have 2 extras around the center. So when you build that one, it's going to look like this. Let's get rid of some of this. Hang on, take that out. And then put in, because it's got 3 shared pairs, unshared pairs around the center, so it's a straight line. It's linear. So it's not number 15, but that's, oh, I did 14, didn't I? Hang on, let me back up. So our question was 14 a choice? No. So I did 14 by mistake. So let's do 15. Sorry about that. 15, CO3. All right, I'm going to draw CO3 on this page because we haven't drawn it yet. So CO3, we had to put the C in the middle, put the O's out here. And we've got 4 and 18 makes 22. 18, 4 is 22, plus 2 more. It's 24. So you got 24 valence electrons. Take away 6. You see what's going to happen? I'll put 6 here, 6 here, and 6 here, and I'm going to be 2 short right there. 6, 6, 6 is 18. I still need 2 more here. I don't have them. So what you have to do is add a double bond. Like that. So then you have 4 here. There, 6, there's 6. How many double bonds are in this picture? Just 1. And that's the answer to that question. Because the question said which one has only 1 pi bond. Let's look at 22. Just to make sure we're on the same page. So 22 was SF4. I thought I had drawn that, but I haven't, so let's draw it real quick. So SF4, put the S in the middle, put the F's out here. I'm drawing it the way I know it's going to look. So 6, 7 times 4, 7 times 4 is 28, plus 6 is 34. Take away 8, gives you 26 valence electrons. 6, 6, 6, 6 is 24. I got 2 more to put in right there. So that's the scenario where you've got 5 domains, trigonal bipyramidal electron geometry. 4 are shared, 1 is unshared. We call that a seesaw. And let's make it so you can see what it looks like. Just take off these and put in these. Oops, take off 2 of those. And we'll put back in 2 of those, and then 1 unshared pair. So there it is. That's your seesaw. And if you look at it from this angle, you can kind of see. So are you a seesaw? So yes. And you can see it on a, like a seesaw on a playground. It goes up and down. And when I move these around real fast, notice they go up here and they want to get away from that unshared pair. All right. So a seesaw. All right, so that's not going to have any pi bonds. All right, next question, which one contains 2 pi bonds? So 2 pi bonds would have to have 2 double bonds or a triple bond. Well, we've already drawn some of these. So look at number 5 and number 11. So here's number 5. It's right here. It has 2 pi bonds. Number 11 has 2 pi bonds. This question says which has 2 pi bonds. Let's try 23. 23. Did we draw 23? 23 we haven't drawn yet, so let's draw it. I'll draw it on the clean page. So SCN. C is going to go in the middle. You're going to have 6, 4, 5, and 1 because of that extra one. So 10, 15, 16 valence electrons. 2, 3, 4, 5, 6. Take away 4. So you got 12 loose dots to put in. 2, 4, 6, 8, 10, 12. I'm out of dots. I still need 4 more because I need 2 here and 2 here. So to fix that, you either have to do a single bond or a triple bond or 2 double bonds. You could do this. I'm not going to take time in this video to get into which one is better, but if you go back and check your formal charges, you'll find that one is better than the others. And I think this one's a better one because this, I'll just tell you. So 5 minus 1, 2, 3, 4, 5, 6 is negative 1. 4 minus 4 is 0. 6 minus 2, 4, 5, 6 is 0. So 0, 0, negative 1. That's your better picture because the overall charge needs to be negative 1, and you want the more electronegative element to be negative. So that's your best picture. How many pi bonds? 2. 1 here, 1 here. All right. The other choice on this was 28. So you're already starting to see what the answer is. The answer is all of them. So ICN looks like this. You'll end up having the same 16 valence electrons. 7, 4, and 5 is 16. So you'll end up with this picture. And then, oh, by the way, you have 2 double bonds or a triple bond. This one is better for formal charge if you do a single and a triple, because this gives you a formal charge of 2, 4, 6, 7. So 7 minus 7. 4 minus 1, 2, 3, 4. And N minus 1, 2, 3, 4, 5. So they're all zeros, so that's your best picture. 2 pi bonds. So the answer to that question is all of them. Which one looks like a square pyramid? Okay, a square pyramid has to have, let's go here, square pyramid is right here. Oh, it's got to have 6 domains. So you're looking for the one with 6 domains. Oh, I missed our choices. So our choices were 19, 11, 15, and 25. So 19, 11, 15, and 25. So we've drawn all of these except for 25. So let's draw 25 and see if it's a square pyramid. None of the others were. See, SF6 looks like that. That's octahedral. And 11 was just a straight line right here. And 15 was a trigonal planar. It's right somewhere. Thought I'd do it over here. So 15 is trigonal planar. So let's go with 25, see what it looks like. So we got 7 and 7 times 5. So that's 42 valence electrons. Put a Cl in the middle. And put the F's around it. So we take away 2, 4, 6, 8. Oh, it's 5 F's, right? So we'll do that. 2, 4, 6, 8, 10. So that gives us 32 valence electrons to put in. So I'll put 6 here, 6 here, 6 here, 6 here, 6 here, 1, 2, 3, 4, 5. That's 30. So I got 2 more to put in right there. So there's our 6 domains. 5 shared, 1 unshared. And just to give you a perspective on what they look like, there's our 6 domains. And it's called a square pyramid because 5 of them are shared and 1's unshared, and here's your pyramid. See, there's one from here to there is like a triangular side. Here to here is another triangular side on the front. There's one over here and there's one back behind. So it's a pyramid. And it's a square base. So a square-based pyramid. So the answer was 25. All right, so now we've got which one is not polar. Okay, the one that's not polar will be the one where the vectors cancel each other. So 19, 9, 10, 28, and 30. So 19, 9, 10, 28, and 30. Not polar. All right, so we know this one's polar because the electron is going to go toward the most electronegative element, which is that way. They will also pull slightly this way, but this will be a bigger arrow than this because this is a bigger electronegativity difference. HCN we drew on the other page. It looked like this. Right there. Oh, darn. Sorry about that. Let's go back up a little bit. So ICN looks like this. And the electrons are going to go toward the more electronegative element, which was the N. They'll go this way a little bit, but this is a bigger arrow because the electronegativity is different. All right. Then the HCN looks like this. Electrons are going to go toward the more electronegative element, and they both go. So this will be more polar than this one because this one is the iodine's pulling them back slightly. CH2O. We haven't drawn that one. I'll draw it real quick. If you draw it out, it'll look like this. Electrons are going to go that way and that way, so are they going to cancel out? They're not going to cancel, so that means it's polar. So remember, if the arrows cancel, it's not polar. But that one's polar, and that one's polar, and this one's polar because the arrows don't cancel. So then we have 30 and 19. I haven't drawn 30 yet, so let's draw it. It's got Cl in the middle. You'll have some O's off of it. By the way, if you look this up on the internet, you'll see 2 double bonds. I'm going to draw it with 1 single. I didn't talk about that. Sometimes you expand the octet in order to minimize the formal charge. So this is 7. 6 times 2 is 12. 19 plus 7 is 26. Take away 6 gives you 20. 1, 2, 3, 4, 5, 6, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I didn't have to put any double bonds in. That just works. All right, is it polar or not polar? Well, the electrons are going to go toward this way, and this way, but that shape's going to be a pyramid. So the electrons really all pointing in these directions. The arrows are all pointing in those directions, so that's going to be very polar. So that's a polar molecule. Now this question says, which one is not polar? So that brings us back to SF6, which I have drawn somewhere, right here. This is the SF6. So the electrons go that way, this way, and that way. So they're all going to cancel out. And the one up and the one down cancels, and so the whole molecule is going to be non-polar, and that's your answer for that one. So that one's number 19. Okay, next question, which one is polar? Well, we already know it's not 19. So we'll go back and look at 5 and 6. So 5 looks like this. It was a straight line molecule, carbon dioxide right here. So the electrons are going to go this way and that way. So they're going to cancel out. 6 I didn't draw, so that means it is non-polar. 6 I didn't draw, but 6 looks like this. When you draw it, you have to have a triple bond. And these guys pull on electrons evenly. So there's absolutely no poles on this. This is a pure nonpolar situation. Okay, we want to know which one's polar, so let's go to 11 and 14. Okay, 11 is CO. CO is going to be those. Oh, that's not going to. They don't cancel. There's nothing over here to pull the other way. So that's your answer. And the other one was 14, wasn't it? Yeah, 14. So 14 was XEF2. It's a straight line that way, that way. So those guys are going to cancel. So that one's not polar. So the answer to that question was CO because the vectors don't cancel. All right, I'm going to skip this one here. I talked about this one a minute ago. Sometimes, like if you draw SO3 like this, we drew it with one. Sorry, I keep forgetting to switch back over here. Sorry about that. Okay, so we drew it like this with one double bond. But if you look at the formal charge on the sulfur, that guy is got 6 valence electrons. Take away 1, 2, 3, 4. Half of the shared, that's 4. There aren't any unshared. That gives you a formal charge of 2. But if you look this up on the internet, you'll find it looks like this when the pictures that pop up. So what we've done is expanded the octet and made 12, 2, 4, 6, 8, 10, 12. Of the 24 valence electrons, we'd have 12 in it, so we'd have 12 to put in. 1, 2, 3, 4, 3, 4, 1, 2, 3, 4. And that would be our picture. Now if you did the formal charge on the center atom, you have 6 minus one of these, 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 and one of these. So that's 6 minus 6, and there aren't any unshared, so you just have 0 for the formal charge. So by expanding the octet, you can minimize the formal charge. And that's what that question means. So that one would be, the answer was element number 20, or compound number 21, which was ClO3 with a -1 charge. So 21 is this one. If you just draw ClO3, if you just draw ClO3 according to the rules, you'll have Cl like that. 7, 18, 25, 26. Take away 6 gives you 20, so you'll end up with like that. So but the formal charge on the chlorine will be 7 minus 1, 2, 3, 4, 5 is positive 2. If you draw it with 2 double bonds and change these electrons around so you don't have them here but they're sharing them instead, then you expanded the octet 2, 4, 6, 8, 10, 12, but the formal charge is minimized. All right, that's what that question meant. Higher boiling point, the bigger ones have a higher boiling point. So which one's the biggest? That one. These goes back to the labs. We did these 3 alcohols. This is the one that evaporated the slowest, and so its boiling point is the highest. If it evaporates slower, it means it takes more energy to separate the molecules, so the boiling point will be higher. Here, I've got a polar small molecule and then a huge nonpolar and a small nonpolar. Well, we learned, this is the 3rd lab we did with boiling points. And in that lab, we had a nonpolar C6. Let me show you what the 2 chemicals were we had. We had C6H14 and we had CH3OH. And we also had water in that one. We found out that these two were pretty similar, even though this one's nonpolar and this one is polar. It's the fact that this guy is so big, it makes it, remember the electrons sloshing around that I showed you, had that little animation with the spheres, the orange spheres. Maybe I can show you how to do what I'm talking about here. This was that thing from Oklahoma State University. This shows 2 polar molecules interacting with each other. But remember this little picture, and we get over to here, see how they keep reversing their directions as it progresses. They start repelling each other, and then the polarities begin to change like that. So they're always changing. And the more molecules you have, the longer it takes them to flop back like they were originally, so the dipoles are longer lasting and makes them stick together better. So in the lab we had, these two were similar. This one's bigger, this one's smaller, and the bigger one was about the same as this small polar molecule. Then we had water that was a special case, and we talked about hydrogen bonding there, where the water molecule attracts like that, and the hydrogen bond is between, I didn't draw that very well, hang on, let me draw another one here, like that. The hydrogen bond's right here, just a positive negative attraction between the H and the O. Then you couldn't see that very well. Let me do that one more time. So we got HOH, and we got HOH like that. Okay, the attraction between the molecules is right here. That's called a hydrogen bond. And that one is a really, really strong bond as intermolecular bonds go. All these intermolecular bonds are weak, but that one's the strongest of the weak. All right, so now back to this question. Which one has the highest boiling point? Probably going to be this one, because it's way bigger than this one. So the answer was that one. Okay, how many electron domains in molecule 14? Okay, molecule 14. We go back and look at it. Did we draw it? Yes, we did. So molecule 14 was this one. So electron domains, 1, 2, 3, 4, 5. So the answer to that question was 5. Next question. Center atom with sp3d2 hybridization. So you need to pick the one of these that has 6 domains. The answer was number 26. Be sure that you understand why. Draw the dot diagrams. It's the one with 6 domains. Linear with an expanded octet. So you draw the dot diagrams again. I've drawn that one for you. It is linear with an expanded octet would be the XeF2, because there are 1, 2, 3, 4, 5 domains around the center, which means there's 10 electrons, and that's more than 8. And it's linear. Okay, the hydrogen bonding, 8, 10, 3, and 9. Just drew a picture of hydrogen bonding, and that was number 3. Remember, hydrogen bonding occurs between molecules, like this, between the molecules, when inside the molecule you've got hydrogen bonded to either O or F or N. This molecule, these water molecules count as hydrogen bonding between the molecules because the H is bonded to the O within the molecule. So if that was an N, you could still have hydrogen bonding, or if that was an F, you could still have hydrogen bonding. But these 3 elements are the only ones that are electronegative enough to pull the electrons away from the hydrogen in order to create hydrogen bonding between the molecules. All right. I rushed a little bit at the end there. I thought you were getting the hang of it perhaps, and this video is getting long. So hopefully it was helpful, and then of course we'll take questions again next week. It'll be on Thursday. And that's the end, I think, of all I'm going to say about it. All right, we'll let it go there.